Lucas Hamilton, welcome to Building Science Digest. Today we're going to talk about moisture management. Thank you for being here with us today. You've been involved with CertainTeed for 21 years, but the building science industry for 25, I believe. What started you off, or what gets you interested into this field in particular?
When investigating problems in the field, actual project failures, and trying to figure out what happened, because it wasn't supposed to happen.
Right. And moisture, I'm assuming, played a pretty large role in what wasn't supposed to happen, right? We don't want moisture to develop. With that being said, what particularly about that made you more intrigued in the building science and the building envelopes?
Some of the first things I looked at weren't supposed to happen, but should have been predicted.
Yeah.
Once we fully understood them, they should have been predicted. It wasn't a human error in terms of the construction. It was a human error in terms of material selection and an ignorance of a property. And that's when it started to dawn on me that you can't look at a single property of a material and get away with it. You have to look at all of the properties of the material, because when you start putting things together, these properties influence everything around them and the materials around them. And so what I was initially seeing was some changes in the balance of the building that shouldn't have been occurring because an oversight was made in the properties. And so that really opened my eyes to the fact that there was a really fascinating and complex thing going on out there that could be really, really cool and interesting to get into.
What was one of the first things you noticed that wasn't matching up, right? You mentioned the envelope and everything needs to be working as one in unison. What was one of the first things you noticed that wasn't essentially playing its role?
So for me, this goes back a few decades now, back to the last century, but it was in some resorts in the South of the United States. Back at the time, all of the interiors of these rooms had interior color schemes that had red and pink in them. And it was almost disgusting to me,
Okay.
but there was a reason for it. And it was to hide the pink bloom that was going on behind the vinyl wall coverings in the walls, that when the mold was breaking out behind the wall coverings, it was actually coming through the vinyl wall coverings as a pink color scheme. And so they found that by using pink colors in the rooms, it wasn't as obvious that this was going on. But once you became attuned to it, you really couldn't miss it. And then you started smelling it everywhere you went, and then it drove you crazy. But that was sort of like this aha moment to me that was like, there's a thing going on here, and people are finding a way to work around it with regards to how to keep the room rented, but it wasn't solving the problem in any way. The problem was
trying to get away with it.
Exactly, they're trying to get away with it rather than solve it.
Okay. Yeah. So you mentioned solve it. So what are some of the first things that people might not realize how important it is in general, moisture management? And then what are some high-level things that we can do as a business, as a company, in our daily lives to solve said moisture management problem?
Maybe one of the most important concepts to start with is that almost every material has a safe moisture storage limit, and that almost everything can get wet, and wet to a point for a certain period of time. And so you've got this equation of how much moisture is in something for how long, and that's also time is influenced by temperature. And so then once you know all these things, now you can start sort of predicting what I should use or creating designs based upon how wet a material can become. We really understand how moisture flows and the forces that drives moisture. And so with an understanding of how much moisture they can accommodate, now you can create assemblies that will accommodate moisture flows. There's basically two kinds of buildings. A building that's wet and a building that's going to get wet. And so when your building gets wet, what's going to happen with that moisture? Are you going to hold it and wind up in a big bit of trouble, or are you going to breathe it away? Everyone people think about buildings in the past and they go, I really want my buildings to breathe, because they think buildings today are too tight. Well, they're not too tight. And when you say you want your building to breathe, what do you mean by that? Because a building doesn't need oxygen. People need oxygen, but a building does need to respire. It needs to get rid of its moisture.
Right.
And so breathing of moisture is really the big thing. You've got to be able to accept some moisture, accept the fact that you're going to get wet, and dry at a rate, again, which keeps you below your safe moisture storage limits for all your materials. And if you can do that, then you're this living, normal, cyclic thing that's existing in nature without conflict.
You mentioned the safe moisture storage limit a few times there. So specifically, and we talked about this before we started, that quite literally means everything, right? I think a quote you had mentioned to me is everything can get wet. It's not about if it can get wet, it's about how quickly can it dry after getting wet. Is that right?
Yeah, exactly. Because even if you can accommodate moisture for a period of time,
Yeah.
there's a period of time after which you start to suffer from a breakdown of your materials, from biological contamination, which can break out, which is a whole other issue for us in wet buildings, is that we can have mold and things like that, which really impact the people inside. So that really is that equation about moisture, temperature, and time again, which impacts those things. And everything that we make our buildings from and we build our homes and our buildings around us from has this thing built into them. How long can they get wet at what temperature before problems start? And again, this is pretty well known with the materials that we have today.
Sure.
And with some of the computer simulation and modeling programs we have, we can very accurately predict how this moisture will flow in assemblies and look at how a material or how a given wall or how a given building will perform in a specific climate with relation to how wet it's going to get and how it will dry.
So you mentioned specific climates. I think another aspect I want to focus on is the different sources.
Yeah.
Right. In a way, there's not just rainwater, right?
Right.
There's 4 different sources of kind of water penetration, if you will. Could you elaborate on those 4? You've touched on kind of rainwater and the external elements.
Yeah,
but what else is?
So rain's clearly the biggest one,
Right.
and then there's all these different kinds
That's
of rain
the one
too,
that
right?
first comes to mind.
Yeah,
Right.
and then you've got that rain that falls nice and gently on your roof,
Yeah.
and goes to your gutter, and then goes down your downspout and is properly, conveyed away from the foundation of your
Right,
building,
right.
ideally.
Ideally.
And
key.
then you've got wind-driven rain, which is slamming into the side of the building. Now your wall's getting wetted by active rain, and that rain's now got to run down the wall and leave the building. You've also got ground moisture.
Yep,
The
from
water on the
soil,
ground is either running away or running towards your building,
Right.
including the water that's below the surface. If you have a groundwater situation that changes, you can actually have a hydrostatic head of pressure against your foundation walls that's literally trying to pump water through that wall under pressure. And then you've got the moisture that occurs within the home because
Right.
people live within homes and have activities within homes which generate moisture.
Yep.
As we respire, we give off moisture. As plants, animals, evaporating moisture from sources in the home, taking showers, doing laundry, all your everyday activities generate literally pounds of moisture per day into the home. And commercial buildings as well. Think about the activities in there between kitchens, cleaning, all the facilities are in there. So there's moisture produced in every kind of building, and it's a balance between the building envelope. No matter what kind of a building it is, the envelope has to maintain this balance between this interior environment and the exterior environment. It's been designed to keep you comfortable inside. Part of that relationship is moisture, because moisture has an impact on your comfort. And so this envelope's trying to handle all those things and make sure it can breathe without trapping moisture and eventually failing because of that trapped moisture, becoming a durability issue. So, it is a science. But again, the great thing is it's fully understood,
Right.
and it can be predicted, and we can do this really, really well. We can even do it to a degree where we can build in some additional durability to compensate for some unanticipated events. Events like an unexpected rain, like rain happening harder and faster than it was supposed to.
Sure.
Or maybe an error being made in the construction process at some point, letting moisture in at some point where it wasn't supposed to get in. If we can build an additional durability and breathability and tolerance to those layers, then perhaps it won't fail because of that individual issue.
Sure. The 4 sources, those are pretty well known. Is there one that presents a bigger challenge of handling, of planning for, of getting rid of avoiding? It's a loaded question.
Yeah, it's a total loaded question.
Because I think, like we talked about, rain and the rain
Yeah.
is what people think of the most. I think soil is probably maybe not as thought of as frequently. The moisture source being inside the home, right, from the different activities, may also not be as widely thought of. But of those 4, of the 3 I mentioned, and then there's the 4th, but is there one that presents a bigger challenge than the others?
It's so personal.
Yeah.
It literally comes down to the building and where you're at. For some people, it might be groundwater.
Okay.
It might be the fact that the larger rain events are impacting them because now it's overflowing local streams that it didn't before. Now they're in a flood zone and they didn't know they were. And now they're literally taking flooding and have groundwater issues they did not before. Or that same greater rain event could be that they're getting more rain on their roof than they were ever designed for, or on their walls, or in their windows, and things like that. So it can be the rain in a lot of cases. In other cases, like in homes, one of the most confounding ones that a lot of people suffer from is ground moisture coming up as water vapor from an inadequate ground vapor cover through a crawl space or through their basement slab. And so you have people, 2/3 of this country uses air conditioning. Yep. And a lot of people have either their entire home or part of their home over a crawl space. And those crawl spaces are vented to the outside. And when you're running your air conditioning in the summertime, the moisture from the outside is coming through your crawl space and being sucked up into your floor. And all of a sudden you start developing floor problems, hardwood floor problems, moisture problems. And it's the problem is your mechanical system is pulling moisture from the ground and from the vented crawl up into the home. And so there's an instance where it's just atmospheric moisture, and your home's mechanical system is sucking it in places it wasn't meant to, and so you didn't have design resistance there. So again, that's what I mean. That
depends on where you are.
Depends on where you are,
what
kind of a building you're in.
Sure.
But even in an existing building, a perfectly functional 40-year-old building that's never had a problem, all of a sudden the core of the building, you've got massive water issues because copper pipes developed a pinhole leak because of the pH of the water over time developing a hole through that copper. And so basically, if water is anywhere nearby, eventually you have to anticipate that in some way it's going to be a problem, or it can be a problem. So if I get wet here, how will I dry? Becomes the way you start looking at your problems or your issues.
That's interesting. Thank you. So, and it's funny because you can clearly tell that you are so passionate about this and building science as a whole, not just moisture management in the commercial space, but on your LinkedIn profile, you quite literally have, "I love this stuff." And I think that is a great quote. It's not just you've been involved in this industry for so long and you've just kind of fallen into it. You have a deep-rooted passion for this. I was hoping you could maybe talk about why specifically. You already kind of led to what got you into the business, but why do you love this stuff?
Well, first of all, I don't understand how you couldn't be fascinated by the world around you. I mean, that just seems to be inherent. And because I grew up in a family of builders, I've been around this thing of ours, this building of buildings, forever, and trying to understand how it worked, why it worked, and why it worked for people or didn't work for people. That's kind of like the next level of curiosity is, once we can make these buildings succeed, how can we make them succeed for people? How do we make a person succeed inside a building when we were not developed inside buildings? Right. So how can we make the building work for the person, not the other way around?
Right. So it's been just curiosity this whole time.
Yeah. It's curiosity and being very, very thankful that there's a value in what's learned from that curiosity that can be shared with others.
Love that. Back to moisture, because it is so specific in what we're talking about today. We've touched on those 4 sources. I think it's important to bring up not only the sources, right, with the vapor and the soil and the rainwater, but the type of transport process. It's not just vapor diffusion and the convection, right? We're talking about the different gravity flows and the water capillarity that also happens during that process. I was curious if you could touch on those 4 in particular of the process of just, again, transporting water from one place to another.
Yeah, sure. Probably the one that's most common to all of us, because we see it constantly, is gravity. Yeah. That's what made the rainfall to begin with, and that's what is for the most part draining off the surface of our buildings. That rain will, run downhill. Water will run downhill. Now, there's other forces that are going on at the same time. And if you ever notice that not all the water runs downhill, right. Even not all the water runs down the wall. Water gets stuck to the wall. So there's forces there that are stronger than gravity. So at a certain mass, the water becomes basically too thin. And gravity's not going to pull it off anymore. Now, the sources of, say, surface tension are making it stick to the wall. That surface tension will also cause something we call capillary movement, that as it's now stuck to the wall, if it finds a crack or a void or a capillary within that wall or that material, that surface tension will sort of walk that water back that void. We've all seen water walking up the sides of a glass. When we were kids and looked at that. That meniscus is caused by surface tension. That same surface tension is what's walking that water back that crack. Okay. Like it's walking that water up that glass.
Fighting gravity.
Yeah. Right? And it will. It'll fight it vertically. It'll take it back horizontally. It'll take it back a great distance. And so Horizontally, typically we try to break those capillaries. We create cavities in walls so water can't get across them, or we cast a hydrophobic layer or material inside there so it can't get through there. But a lot of the materials that we make buildings out of have capillaries and voids in them. Things that grow naturally have them. Things that aren't manufactured under pressure have them. So they're in a lot of our materials, and so that's how a lot of the water winds up getting transported back into the building is through these capillaries. That which does not drain off from gravity will get walked back into these capillaries. Now, water will also get moved by air. In some cases, it's literally as water vapor in the air is being carried by the air. Airflow will also carry water uphill. Typically, in a lot of our building designs, with the wind pressures that our buildings are exposed to between 90 and 130 miles an hour for the United States, about the minimum distance you'll see water rise protection being 1.2 inches. Because at 90 miles of an hour wind, it'll blow water 1.2 inches up a vertical surface.
Interesting.
And so that's why a lot of our designs start at 1.2 inches or greater for trying to fight
Just
gravity.
in case.
Because wind will try to blow it.
Let's that's a really interesting fact right there. So let's say that again. So for 1.2 inches is the amount of height water will move, given the air or the wind speed being 90 miles an hour plus.
And an example would be if you look at a commercial window and you were to cut a cross section of that commercial window sill, the distance between the weep hole in the front of the window the weep hole, which would be the front where water, because commercial windows anticipate that water is going to get inside that frame. Because they know that water gets past stuff. And so commercial windows have a weep hole drilled in the front so water come back out the front of that frame. So now you put a hole in the front of the frame.
I even think I've visually seen that.
Yeah, you can walk around your building and check out those little holes. Now, you've made a hole in that window now, right? So that can also fill with water. So now you've got this cavity in the bottom of that window, and the distance to the top of the interior stop, which would be where you can get past that whole frame to the interior environment, is a minimum of 1.2 inches. Because that's how high the water will rise in there if you expose that window to a window test, according to the ASTM standards, under the pressures and design loads. That's how far that will fill that window during that test. And so if you're not at least that high, you'll fail. And so
you'll fail, and the consequences of failing is essentially water now gets into
now getting into a place where you did not anticipate it. So there are parts of our buildings, wet zones of our buildings, where we expect water to get wet. We're going to manage water and get it back out again. And if we don't expect it, we're crazy, because we've never managed to create a building where we didn't let water in.
Where
and so we have to expect it's going to get to some point, but from there we fight it and we push it back out again. And those are the wet zones. And out in those areas, we want those materials to be able to take that moisture. Inboard from there, we really don't expect it. We have moisture-sensitive materials like wood materials and metal materials that can corrode and other materials that will be degraded from that exposure to moisture. And from that point in, we try to stay extremely dry.
Is the hole that we're referencing, and that's in the bottom of the window here, that's what we considered a void for the capillary that are we're trying to create?
That's actually too large. Yeah, I'm sorry to jump on you, but that's actually too large. No, this is good. Capillaries get more intense the smaller they get, and the larger they get, it's too much empty in here. The water's no longer solid in the middle. And so now it's just around the outside. But if it can be solid in the middle and touch those sides, now it can rock. And so it doesn't walk its way back through those holes, but it will the window weeps. But it will blow through. If air can blow through there, it's going to push water right along with it.
So the difference, essentially the difference between a capillary and the void is wind being able to get through ultimately and push the water through. And the goal of that, right, as a reminder, is essentially you want to let water in, but you want to make it easily accessible to get out.
You expect
the
more
goal is
water
to get out
than ever get in. Because water will eventually get in. You've got to
and you have to plan for that, right? And that's the ultimate. That's the end goal, is planning for water to get in. So we've touched on roofs and rainwater and the gutters, and now kind of we're inching into that walls and the foundation of moisture management. What, in regards to the walls and the foundation, is it voids? What are other things that can be done, right, from a moisture management perspective to adhere to certain specifications, to standards, to also just be compliant for ultimately what we're going for here, which is just being able to let it dry after the fact.
So what you do below the ground and what you do above the ground are different because of the ground. So the ground's a source, but it also doesn't breathe air. You know, when you've got the air around you, you're going to play totally differently when you don't. And so below grade, some of the best things you do, or if you can get a capillary break between the building and the ground, a place for water to freely drain, water needs pressure to push its way through that wall.
Yeah.
You know, even with a crack in the wall, you're going to need to get water in contact with that crack, even for the capillary to work it through.
Okay.
If you create a void through any kind of a capillary break there for water to drain down and away from the building, it's not going through the wall. Water would have to build up in that void to get through that wall. It really doesn't, water wants to drain away. It doesn't want to take the hard path. And so you give it an easy path away. It typically wants to go away below grade.
Okay.
And so we have leave-in-place forms that we typically, with built-in radon protections, we put our radon and our drain around the building and our radon drain and have everything, you know, flowing away from the building below grade. That's kind of the easiest thing for us to do there.
Below grade.
Below grade.
Below grade, yep.
Above grade, it's a little bit different. The best thing we can do there is to adopt what was considered a rain screen philosophy. And that is that the outer facade of your building, the face of your building, be it the roof or the walls, is really just shedding most of the bulk water and weather which hits it.
Okay.
The real protection is being done by an underlying layer that catches anything that gets past it. So what we do, think of a brick cavity wall.
Yep.
A brick cavity wall has that airspace behind it, and then typically in front of the sheathing, which could be a plywood or a gypsum sheathing, depending upon the nature of the construction, will have an air and water resistant barrier there. That's your real workhorse. That's the one that's really protecting you.
Interesting.
The masonry.
Not the brick wall, not the masonry.
The brick wall is taking the beating of the sun, which
It's just, yep.
That's
That's
need.
a different thing. We have another episode
Oh my
for
gosh,
that, I'm sure.
yeah, save that for a whole other thing because the sun's a killer. And of our building materials, it's the great oxidizer. It whacks everything. And so the brick is going to protect that real workhorse for you back there. That elastomeric membrane that is an air barrier and a properly breathing, depending upon your climate, either breathing or not breathing, water barrier back there that is going to help you. The brick's protecting it, but that's really going to be the part to make sure no water gets past there.
Got it, okay.
And that part drains out. It gets past the brick, it gets past the panel, it gets past the clapboard. No matter what your siding is, you create provisions there for that layer to drain back to the outside again. Now, if you're really gifted in terms of your assembly and your resources and your ownership, that you can vent this as well, now you're in happy land. Because if you can take the same cavity and open it at the top, you've created a breathing assembly. Because if you take this brick cavity wall and you only open it at the bottom and you start blowing rainwater through it, and you do. Research has showed as much as 10% of the wind-driven rain gets past that brick onto the next thing, which is this space back here and this void. Some of it gets into the void, some of it lands on that next layer back there, which could be the air barrier or the water-resistant barrier. When that happens, testing has shown only about half that water comes out. The other half stays sitting in there.
Interesting.
Because it's stuck. It's literally stuck
Because
to the
you're
wall.
saying it's
surface tension.
It's surface tension. It's stuck to the wall, and there's only one way
Gravity
in
can't
and one
pull it
way out. Right?
Yeah, it came in through the crack. It's trying to get out through the weep at the bottom, but it can't even make it down to the bottom because it's stuck to the wall. That which did make it to the bottom, some of it made it out to the weep, and the rest of it just kind of sat here until the sun came out. Now, as soon as the sun came out, that wall got hot.
Right.
Because red brick is as hot as the sun. Now, as soon as that red brick wall gets hot, the airspace gets hot as well. Now, because the air is warming up, the relative humidity of the air is decreasing. As the relative humidity of the air is decreasing, the water starts to evaporate. All of a sudden, even if it's February outside and 20 degrees Fahrenheit inside your wall, it's 80 degrees Fahrenheit, 95% relative humidity. Guess where the water's not going? Outside.
Oh, no.
Yeah. It starts pumping. It starts pumping. And it really starts pumping into the wall.
So what is the solution to that? Because you've mentioned climates now a few times, and it obviously it differs for the climate that you're in. So in this example here, what is that solution? What it is the winter, when you're in a cold climate where it is 20 degrees outside, you've got moisture in the wall, and it's open the top.
Open the top.
Why does everyone open the top and open the bottom?
No one opens the top.
No one opens the
No
top.
one's top. Unless it's a commercial rain screen, then everyone opens the top.
Okay.
But in our residential constructions or in other constructions, everyone sort of forgets to open the top before the next floor. If they would open the top, now when that air gets to be 80 degrees and 85% humidity, it does what warm air does. It rises up and out. And it pulls in cool, dry air at the bottom. And now you got a dry air running through your wall. And there's no penalty for it because it's on the outside of your insulation.
Sure.
So if you've put...
So that means that the insulation also is not then absorbing any of the
It's dry,
moisture,
right?
right? It's dry.
And it's
Yep.
dry, and that's what insulation wants to be. It wants to be dry.
Right.
Once
Once it's wet, it won't.
It doesn't work.
That's right.
Totally easy, passive thing that you can put into a building design that the environment's going to do for you
Yeah.
to help you stay dry, and it works in almost every climate.
And that's a key point there too. So does that affect the durability of the structure at any given point?
The absence of it does.
Okay. The absence of it
The absence
does.
of it absolutely does.
Okay.
Yeah, I've had the experience of looking at different kinds of constructions across the United States prior to joining Saint-Gobain. And I had the opportunity to look at all kinds of constructions. And it was really interesting to me that in certain types of residential neighborhoods, the front of the home is always brick masonry, and the sides and the back of the home are always vinyl siding. And it didn't matter which orientation the house had in that neighborhood. Behind the brick, you found all the moisture problems, and behind the vinyl, you found almost none. And it wasn't that there's a problem with brick. The problem wasn't with brick. The problem was with how the houses were being constructed, that those cavities were not draining and venting. Yet behind the vinyl siding, because the vinyl siding is inherently loose-nailed, because it has to expand and contract,
Because it has to move,
it
right?
drains and it breathes. And so there's no moisture problems going on behind the vinyl, which is conceived as an inexpensive, lesser cladding because of the fact that it's made from polymer, not from masonry. However, all the moisture problems were behind the really expensive masonry just because it wasn't being given a chance to dry out. It wasn't being given the full-blown rain screen treatment that it should have. When we do those kind of walls, they absolutely should be open to top. We should be taking some of the vents and putting them up to top to make sure that wall can breathe.
And you're referencing residential currently, and you mentioned it before, but the void at the top does exist in most or all commercial?
It should if it gets inspected and someone
Okay.
has it designed in and drawn in and talked about.
Okay.
In traditional
But it's
practice,
for residential, it's not as popular. more
right?
or
But
less.
even in commercial, if you're not looking and you're not paying attention, you could not get it as well.
Okay.
Just because you've got to say to someone, listen, here's what I want and here's why I want it. It's really easy for them to leave it out because I didn't put it on most of my jobs last year. It's what they're thinking.
Sure.
Well, someone didn't tell me
Why
to
would
use it,
I
I'm
do
not
it?
going to use it. There has been explained to them why it's so important for them to use it.
Got it. And that plays a role in the overall, what I would consider the energy efficiency, right? If you're drying your house or you're heating your home or cooling your home, if you have that air barrier in between, let's say mortar, right, brick and mortar, and the membrane, that's probably going to become more energy efficient for your home at the end of the day.
Well, yeah, the air barrier is the colder your climate is, the more important your air barrier is with regards to energy consumption. Yeah. Because hot air wants to leave your building. So all the air you're paying for, literally, in a lot of our old homes, 5 to 6 times. If you have a house built before 1970 and you've not done a renovation to it, 5 to 6 times the volume of your house leaves every hour.
Ooh. In
An hour.
every 10 minutes. Hot air, essentially.
Yeah,
In hot
every
air,
10 minutes, all the heating you've paid for just left, and you're paying for it all over again.
5 to 6 times the volume of your
crazy.
home
Yeah.
is leaving, in regards to hot air, is leaving your home
Per hour.
per hour. Once
Yeah, when it's at peak cold
When
time.
it's at peak cold
So that's just energy. You might as well just be burning your money and sending it out trying to stay warm. So that's why we have air barriers in the building code today, why all new homes have air barriers as requirements. And that air barrier does totally reduce the amount of airflow through the wall. That unfortunately does also change the moisture balance of the home, because in the past, when you didn't have air barriers and you didn't have insulation, that wall is a lot warmer.
Right.
And things that are warmer are drier. When they get cold, they get wet. And so
And they stay wet longer.
right, so if you insulate without proper use of air barriers and without proper use of vapor retarders, you have moisture problems. But if you do it properly with the right control, you absolutely do not have moisture problems. You are more energy efficient, more comfortable with better air quality, because the fact is the air barrier prevents accidental air infiltration. For every cubic foot of air that was accidentally leaving the home before, you had a cubic foot of air that was coming in, but it wasn't coming in the right way. It wasn't coming in through a filter.
Sure.
It was coming in through your wall. Your wall's filthy. And so you're basically like, might as well get down and just like breathe next to your baseboard, because that's what you were doing. And so it wasn't the right air to get. Now, with air barriers, we use energy recovery ventilators and heat recovery ventilators. We attach them to the building, to the home, to bring fresh air in through the mechanical system, to exchange the hot or the cold with the outgoing air that we're pumping out, so we don't lose energy.
Right.
We exchange the energy as they pass each other, and then we bring in the fresh air.
And this is a great example of how essentially the air management and moisture, it can directly correlate to the moisture management of a building, right?
Yeah.
Everything is ultimately coexists.
They coexist,
and they need
because
to coexist, because if they don't, then you're going to have problems. And gosh knows what
you'll be
else.
out of balance, right?
You'll be
out of balance breaks.
You'll be out of balance. That's
Yeah.
a great point there. I want to ask you about Dr. Straub and a few articles that you've mentioned and brought up to us here before, and just what he's done not only for kind of the industry, but moisture management. It seems that this has been his MO for a long time. And what things have you learned that you can share with us today?
I think one of the great things about Dr. Straub has been his evidence-based opinions, that he's based it upon experimentation, that he's built the walls, he's tested them, he's measured in order to find out what was going on, and that is a really important part of managing the situation. And some of the things that he's measured and that we've learned have been absolutely astounding. I already mentioned the rain penetration of masonry walls, things like this that he's measured, that we've been able to now to incorporate into modeling programs that we use by taking this information as, say, a wind-driven rain penetration, and we can equate it down to a percentage of coming into the wall, and now give you a much more accurate simulation of the future for this assembly. Sure. His research has helped us simulate the future so much more accurately than we could have without that.
It's the balance that overall plays that bigger role in essentially the process of building, whether it's commercial or residential. It's the balance of getting wet and then staying dry.
Yeah, it's that it's presenting it in that light. I know there's a great graphic out there, with a bucket with holes in it and spigots and things like that, and a line across with safe balance. And these are the kind of things that I think in the way that he presents that information that helps us understand it so much more clearly, without the complexities that are available beyond that.
Sure.
As you start talking materials, people, they can get as absolutely complex as you want, and certainly more than you need to with regards to this conversation. And so that's, I think, some of the things that he's done are so cool, is that he helps keep it at the level it
doesn't need to be complex.
It doesn't need to be as complex as some people necessarily would want to talk.
It is a science. It is a science, so it is complex without a doubt.
It is, and it's fascinating to researchers at a level with regard to some of those issues about water and what water does, because water at a microscopic level is fascinating.
Yeah, absolutely.
But at a macro level of talking about our buildings, sometimes some of those things, they're real, but they're not real important. You know what I mean?
Mm-hmm. This has been great. I think there's a few things that I want to touch on. ASHRAE, the standard, the 55s, and I want to get into that, and the building envelope and HVAC and the comfort essentially that surrounds that. Could you speak more towards or more about the ASHRAE itself, and essentially what cascades from there?
Sure. So ASHRAE is the American Society for Heating, Refrigeration, Air Conditioning Engineers, and so it's a society of technical people. And I always say, thank goodness they're out there, because they measure the immeasurable. They measure all the things that we don't want to have to go measure. But with those measurements and with the standards that come from that organization, we are able to manage our buildings and the engineering of our buildings. And so that's really what it contributes. And in a lot of those things, it's kind of funny, like you mentioned ASHRAE Standard 55, which really is about our human comfort. So ASHRAE Standard 55 is an interesting example of maybe one of the more interesting ones that I've come across of an ASHRAE standard, because maybe you're probably different. I'm sure you're different, and I'm sure your parents never told you lies growing up. But I think my parents told me quite a few, and one of them was that I was special. Because according to ASHRAE Standard 55, I'm not. I actually fall within the percentage of about 80% of our population, and that we can define what makes you comfortable with regards to the temperature, the relative humidity, the airspeed.
Okay.
Now, for 80% of us, that will be true, and that's what we shoot for in our buildings. That's when we talk about where does comfort need to be in the springtime versus the fall.
Yeah.
Everything's built into this. It's not extremely simple. Because just when you want to get simple, you have to remember this is ASHRAE, so we're not going to let it be totally simple. Sure. We have to come up with some complicated things. And so we have to talk about things like, but people are different, and there's things that make them different, like age. And there's things in you physically to change over age, like your metabolism, which changes that may your heat you're generating, and so how you feel based on that. Yeah. And then we got things like seasonality and fashion, and the fact that we wear different clothing. Yep. And gosh, this has an insulation factor, so we have to develop an R value, an equivalent R value for clothing. We'll call it the CLO, C-L-O.
Oh,
It's roughly 0.8 Rs.
Okay.
In case you're curious. And by the way, seasonally, we only once we take off our outer garments and we come into the building, we only change about 2 Rs
okay.
in the clothing we wear throughout the year.
Is an R a 0.1 R or is it
As an R value?
or
like,
just
yeah,
one
like,
R
like
value?
oh, you got an R13 piece of insulation in your wall.
Yep.
An R value 2 clothing changes all you do in the course of an entire year. So the clothing you wear doesn't have as much of an influence on your comfort with regard to the R value as you might think. This is built into this discussion about comfort, how much clothing you're wearing, what time of year it is, how old you are, what gender you are. And within that, we can create a parameters for a building performance within which 80% of the people should be comfortable. And ASHRAE Standard 55 is about that. It's trying to define those parameters which would create a space in which 80% of us would find comfort. And I know we think that it's all of us, but no, there's not. There's still going to be about 20% of the people that are going to go,
Right, because
no,
you said
I'm
80%.
I'm just still not comfortable.
Okay.
And you're going to have to go, I believe you.
Okay.
Because even if you're comfortable, if someone else isn't, you just have to believe them.
Yeah.
You know?
Yeah, it's natural. So, so give me the numbers again. So it's 80% of people, we know what their comfort level is. Is that essentially based on ASHRAE 55?
If we can design and operate our building within those parameters of ASHRAE Standard 55, 80% of the people in the building should report that they are comfortable.
Okay.
Sorry to flip your words on you, but I just want to make sure that we say it accurately.
that's right. That's why I want to bring it up.
I can't say that ASHRAE is going to tell us what makes us comfortable, but it's saying that within these framework of temperature, relative humidity, airspeed, how much contamination is in the air, and things like that, that within these limits that we will be comfortable.
80%,
Relative humidity is a part of that. I don't have to mention, but relative humidity is a part of that because the temperature and relative humidity, how your skin, we don't really know what's going on in the world. We only know how we experience it at our surfaces.
Sure.
And so what's happening right now with the temperature in this room, as far as I perceive it, has a lot to do with the humidity in the room. And so as we change that, it changes the way I perceive things. And so that's why it's also built into that standard.
So how are you perceiving the room right now?
Perfect. This building's amazing.
This building is amazing.
This building's amazing.
You talked about relative humidity. Is that the only aspect from a moisture management that plays a role in the standard 55?
No, there's nuances in other places, but actually jumping onto other ASHRAE standards is really, you'll see it pop up, and there's be standards where you go, wait, what's it doing over there?
Okay.
Like ASHRAE Standard 62, which is about air quality.
Yeah.
So 62.1 is for commercial buildings and 62.2 is for our homes. And built into ASHRAE 62 is a discussion about vapor retarders, air barriers, and moisture management because of the impact it has on air quality. Because as the most relative humidity of the air changes, it changes what's in the air. Volatile organic compounds change their reaction and emissions based upon relative humidity. The things that live with us in our spaces that we don't like to think about that are around us all times, like things like dust mites. The waste products of dust mites changes based upon relative humidity, and people actually have allergies to that. And so all of a sudden, a change in relative humidity could change someone's allergic reaction in the room just based upon the production of the waste product of some small mite living in the room. I mean, there's things like that we really don't think about.
No, you would
but
never.
It's such a living thing that we're a part of that as these things are influencing us, again, what the ASHRAE standards are trying to do is identify a series of parameters around which most people will be successful. And that's what the standards are meant to achieve.
Successful,
Comfortable, but also successful in terms of healthy.
Okay.
Because sometimes we're comfortable in situations which aren't necessarily the most healthy for us.
Good point.
And so it's kind of limiting it down to what's healthy for you.
So there is a distinction between comfortability and success. Essentially,
Absolutely.
Interesting.
Absolutely.
Interesting. With all that being said, I think dust mites were mentioned there. What are unique identifying factors from a commercial or a residential standpoint that a builder, a building designer, architect can use to identify potential problems that are currently happening around them? The process is complete.
Yeah.
The building now stands, whether it's pre-existing or it's a new one. What kind of things can building managers do to identify those signs of kind of unwanted moisture, as we call it, right?
For start, let's accept that we're pods.
Okay.
Portable organic detection systems, right? So use our senses,
Okay.
right? If you see things moving, why is it moving? That's typically airflow, right? In a lot of cases. Why is that thing? Is that airflow?
Right.
Do
It's
you
supposed
see-
to be there.
Right. Is that supposed to be there?
Sure.
Do you see dust along the edge of a room along the baseboard? I see dust right there, but I don't see it over here. Why is there dust right here? Let's get curious. Chances are the dust is right there because there's air leakage occurring right through that section of wall, and the carpeting's acting like a filter and catching all the dirt as the air passes through.
Oh, wow.
So we see the indication of the airflow in what's been left behind.
Okay, I want you to say that again because that kind of blew my mind. If one panel does not have dust, let's just go through that once more.
So we're looking at a section of our wall,
Yes.
and we see one area is really dusty, and we see an area that's not dusty.
Yeah.
Don't we wonder why that's dusty and that's not, when we know the same vacuum cleaner and the same edger is doing the
Right.
whole room? In most cases, the reason that's being contaminated is there's an additional source. And so what's the source? In a lot of cases, it's airflow. And carpeting is the most beautiful filter to show you this. If you
Interesting.
look at your home, when you go
Yep.
home tonight, if you have an enclosed garage, look at the passage door from the enclosed garage into the home. If there's carpeting there, look at the carpeting. It'll blow your mind. If you have a basement, look at the carpeting at your basement door, because chances are you've got a return that's pulling air under that basement door, and your carpeting there has a dark line on it. It's catching all the dirt in the air that's flowing through there. And so the dirt is an indication to us that's an airflow location.
that is so
And so
interesting.
when we see insects, when we see spiders
Yep.
in exterior walls, spiders love holes. Spiders don't want to live in your home. They want to live outside your home, but they need to get in and out, right? So they're near a hole. They're always near a hole. Nature is a great indicator to us about
Things
what's
I've never
happening.
thought of.
If we
Spiders
get
need
curious,
to be near
moisture, right? So
Yeah.
moisture. If you're colder than the world around you, you're typically wet, and you're hotter than the world around you, you're typically dry. And so when you see wet stuff in your world, wonder why it's wet.
Yeah.
Is it colder? Why is it colder? If you one window that's showing you frost and others aren't, why is that one showing you frost and the others aren't? Now, chances are it's an air leakage problem with the window too, because in all the things that move, eventually those do become air leaky. And so the more windows are used, those eventually become more and more of a problem for us. But with our walls, those shouldn't be moving. Those shouldn't be air leaky. Those are
Right.
intended to be airtight.
But from a moisture standpoint, I know at the top of this you brought up the looking at walls were painted pink, ceilings were painted pink,
Right.
because that's a way to blend, or they were
Biological,
trying to
right,
hide
the
mold.
biological
Yeah.
color of red and pink is really big in the molds that grow in things that have starch. And so a lot of the wall covering pastes are made from starch. And so that was the color you got a lot with those.
Okay.
But water has other properties that make it really sticky. And so stuff sticks to wet stuff. And so wet stuff gets dirty.
Okay,
And so
yeah.
look for things that have a different reflection of light off them. Typically there's a moisture issue at the surface there. Could be a cause.
Sure.
If it's dirtier in one place than others, typically there's a surface issue there that's either moisture or something else that's trapping the dirt at that place. And so it's all those things about what makes that different. Why is that different? If it wasn't different before, what changed? And sort of leave yourself down that path and get curious. And before you know, you're going to be a building scientist chasing moisture.
And you're going to be in the industry for
Yeah.
25 years.
Yeah.
And that's why you love this stuff.
Yeah,
That's
we do it
great.
together.
So it's essentially, it's being curious, right? I look around the room that we're in now, and I thankfully don't see any spots.
We're
right?
in the
That's
core
a
of the
good
building
thing,
too,
right?
so yeah,
Yep.
we're good.
But with that being said, right, take this building, for
Yeah.
example. There are different factors that went into play in the building we're currently in, or compared to a indoor swimming pool. Walk us through the planning and what goes into a building like the one we're in currently versus what goes into, from a moisture management situation, to say an indoor swimming pool, right? An indoor swimming pool, there is quite literally moisture inside, and our goal is to not bring moisture in or allow it to get in. We want it to dry out. So, right, two very distinct and contrasting buildings.
So your envelope is meant to be your layer of control between environments. So if you only have two environments, the inside of your building and the outside world, your envelope only really has to deal with those two environments.
Okay.
We're going to have one set interior conditions, ideally designed to ASHRAE Standard 55 in terms of our temperature and our relative humidity and our air speeds, and designed to ASHRAE 62 to make sure that our air quality is right. We have the amount of right fresh air ventilation and things like that. But once we have all that working, our mechanical system working, and it's based upon the design of our building envelope, it's a somewhat more simplified situation than your second scenario, in which you now have a third environment inside
the inside.
of the inside. Right. So hospitals have this problem. Schools have this problem. Health clubs have this problem. This problem is very common that we have multiple environments. Museums have this problem. We have multiple environments between display spaces and storage spaces and office spaces and galleries.
Yep.
And so when you have to create multiple layers of control within the building, you can do that again with the envelopes. You pour more envelopes inside the building to control between those. You're really only controlling between two environments.
At any given point, it's two environments.
It's still just two environments.
Right.
The real challenge becomes for your mechanical team now, because they've got to make all those different environments hold those conditions, and for the mechanical system to be able to do that and do that now efficiently and durably.
Right.
And that, hats off to them. That is a tremendous thing to accomplish.
It's a heavy lift.
They have to work with all those layers of control and understand them and understand what the flows will be across them to understand what they have to compensate for. And then again, try to do that with as little energy as possible is their challenge now.
Interesting. Yeah. So it's always always looking at working between two environments, and then the building envelope is specific to each environment.
When I say that the envelope, I'm really going to be talking about all six sides of the building itself.
Yeah.
Its lid, its walls, and its bottom, and inside that envelope, we might have other climates. Like if we have a natatorium for a swimming pool, or we have, if it's a museum, or if it has specialized interior environments for R&D, hospital ORs are kept under very specific conditions.
Yep.
Those have smaller envelopes inside of that larger building envelope.
Understood.
In an ideal world, your building envelope could be stupid. It could be absolutely draconian. It could be a wall. You could build the Great Wall and no one would ever get around it.
Yeah.
But it's never worked. It's never worked. And so we can't act like it's going to work for us on our job. We have to assume that it's not going to work, and that we're going to have to accommodate some breathability, some movement, and some sort of like cyclic behavior. That we can't just be one thing and get away with it. And so that's why the creation of balances is more important in understanding of all the flows and achieving that balance, because we never create a barrier. And even if we do create a barrier, it won't get maintained.
Right.
It'll fail.
And that's why the end goal is, it's not to keep things out. It's water will get in, and it's about things will get wet. It's about how long will it work until it gets dry.
Can we accommodate it with durability and sustainability and create an environment where people are thriving inside? If we've done that, then we've hit a home run.
You mentioned, if you have a home from the 70s or a building from the 70s or essentially older homes, what are things from a moisture standpoint, right, to stay on topic here, that we could do to almost retrofit existing buildings that are currently out there?
So retrofitting a home to make it more energy efficient cannot be done ignorantly, or else you're really going to get in trouble. You cannot just go ahead and wrap a home in a cooler and get away with it. It starts with tightening up the building envelope to reduce the amount of air leakage that's occurring in the building envelope. And that's easiest done when you're re-siding, when you can get behind the siding to the underlying layer. That's the best place to get continuous at. And then once you've tightened up your building envelope, now you can start adding insulation in a way which will not trap moisture. Add insulation in a way which will breathe the moisture and not accumulate it. And then once you've done that, now you can scrap your mechanical system. Now you've got a totally tight building envelope that is energy efficient. Now you can bring in a much smaller mechanical system that is going to be properly sized to your now more energy efficient building, and put on fresh air ventilation with that new system to give you clean, dry, comfortable air at the prescribed rate. Probably more air than you've ever really clean air you've ever enjoyed in your home before. And make the home much, much more comfortable. And it's kind of, so it can be done all at once. If you're fortunate to have the resources to strip off the siding and go after the walls all at once, go for it. But if you can't, start slow, start air tightening the home, then insulate it, then change out the mechanical system.
So you wouldn't say that plugging in 10 dehumidifiers in a basement would be probably a good idea? Right.
It's a
because
very
you mentioned, right, we want below grade, and that's where moisture comes. There's only one way to get in, one way to get out, rather than right what we talked about above grade.
That's a very temporary solution, which is very energy intensive and very maintenance intensive. So I'm going to recommend don't do that, because most people won't maintain the drainage of those systems, and so they become biological breeding grounds. They're really, really bad systems in most people's homes. A better system for they have foundations. Most people are not going to excavate outside their home to waterproof their foundation unless the foundation is failing.
Yeah.
Then financially they're going to be driven to have to do it.
Yeah.
Otherwise, they're going to look for more affordable ways to deal with it. And ventilation is a great way to do that for your basement. If your basement, you can't do this for a finished basement, but if you're living above your basement, what you can do is ventilate your basement. One of my brother-in-laws has actually done this, where you have a system which brings fresh air in from outside the home to the basement floor and takes it back out the top. So you've got fresh air coming in below, rising up and out of the basement, and then the air barrier across the basement ceiling. So that none of this is going on below the home, below your thermal envelope. His ceiling is insulated. It's airtight. All this is now going on down in his old rubble foundation basement where his mechanical system's at. And, so he's insulated the ductwork. We've done a good job of tightening up all of that to reduce the energy loss from that. But we're not going to try to fix this horrible old foundation. So instead, we're getting airtight above it and breathing and getting all the moisture out of that foundation by constantly keeping airflow through that basement area. And it also helps with radon, which is another big problem for us in this area. So what we've done is basically been able to dry out the basement of the home without having to do really, really intensive things above. But to make it efficient, we had to insulate and air seal the lid of that basement so the home above was kept comfortable, and all the airflow and all the crazy things we're doing below there, basically making it like a vented crawl space now, weren't going to make it uncomfortable or inefficient above.
So we just touched on the pre-existing fixes, right, to the older homes. I want to shift to almost the ever-changing climate and how the increase in rainstorms has affected this industry, your industry, and the moisture management prophecy, and then take it a step further and say, what does the future look like in this environment?
Our building designs and the different codes and different aspects we have that set our building design for us. A lot of the water drainage from our buildings is actually in the plumbing code, which I think is inside your building, but your gutters and your drainage is actually out there in the plumbing code. And those are based upon historical weather events. The 1,000-year storms are occurring every year. And we had a 1,000-year storm occur in the Carolinas last year from 3 storms that came together. They were unnamed. And so what we're getting now is we're getting rainwater coming faster than it ever was before. And so it's overcoming our designs. We weren't anticipating water to come at us this fast, from our roofs and from our slopes and on our buildings. And so what's changed for us is that we've sort of got to over-design now. We've got to expect that, the 3-inch overlap on our water-resistant barriers or on the return legs of our flashings might not be high enough. And it's not high enough anymore that water is flowing over it now. And so we've got to start increasing those because we have to anticipate that the amount of water that can fall in an hour is greater now than it was before. And that's just with regards to liquid water. Now you're getting thunderstorms coming further east, which is changing hail, which is causing damage, which is causing moisture to get in. So things have changed quite a bit as the weather has been changing. It's been changing our durability from the amount of water that's hitting, but also from hail impacts, because hail is occurring further east and in larger volumes. Class 4 resistance to hail is now something you really want almost everywhere.
Everywhere.
And because once your roof becomes damaged and the granules start to come off of your shingles, now your shingles are going to start to fail. Now water's coming in, and you usually don't realize it until it's too late. And so building in the kind of additional durability of the building materials, in addition to the design changes that we can make to accommodate these changes in the weather, is upon us right now. We're already doing it with materials. We're creating more hail-resistant, roofing materials and better flashing, fully adhered air barriers, water-resistant barriers for residential construction today, where we used to take house wraps and staple them up. Now today we're fully adhering to house wraps so that in case the siding does get ripped off after a tree hits the house when it comes down in the wind, that house wrap that's behind that siding, when the house wrap siding got ripped off by the tree, the house wrap is still stuck to the wall, protecting the wall. And so there's all additional things that we're building into the materials today that we see coming. It's happening now. So it's starting with the materials. If design
starts with the materials, are there standards or specifications that you think we'll need to keep up?
So there's code and then there's standards.
Sure, yeah.
Standards are, for most cases, above code.
Yep.
code for a large part is a life safety document. It's to make sure that structures are created in a way which is safe, that people are not endangered living in or using those structures. And outside of energy, that's largely where code stops, is that life safety stuff. And then energy is built into it in regards to energy efficiency. But beyond that, durability isn't too hard on the code. Part of the issue is that the code is largely, it's a consensus process in which builders, code officials, architects, everybody in the process has a say in the development of those documents. And so the documents develop a lot more slowly necessarily than culture does. Things change out in our world faster than building code does because of the nature of code. And that's why we have standards, because standards can come along to accommodate change. The reason we have sustainability standards like LEED today is because code could not change fast enough to accommodate what culture wanted to happen in buildings. And so we had LEED come along to create a cultural standard that we can have buildings that meet the standard we want from those buildings beyond just life safety, for sustainability, for comfort, for all of the other things that build into programs like LEED or WELL or the Living Building Challenge. So those standards are out there today. And when it comes to durability and moisture, there's a great one from the insurance industry champions called the fortified home. You can build a fortified home down a really popular option to do along the Gulf Coast, where insurance companies know that they're going to hemorrhage, but they're going to reward you if you build a home that's going to be more durable. So if you enter into a relationship with your builder who's qualified to build you a fortified home, you can get a reduced rate for your home because your insurance company knows their risk is greatly reduced for you to build that way.
Based on the materials
and so,
that you've used,
but you don't have to be going for that insurance. You don't have to live on the Gulf Coast to build a fortified home. You can build that anywhere. And that's going to add to, what you expect to happen in the Gulf. Increased wind resistance, increased wind-driven rain, hurricane resistance, and higher wind resistance are going to come with that. So those are going to be built into that kind of a home. So those are out there today, and we can continue to look that way, and we should look that way. Don't wait for code to come, because it would be a frustrating thing to wait for.
You kind of be behind.
Yeah, it's be frustrating.
Lucas Hamilton, thank you for joining us on Building Science Digest by CertainTeed. It was a pleasure having you today. I loved our conversation. To all of our viewers and listeners, please like and subscribe anywhere that you listen and watch your podcasts.